Good morning, everybody. Welcome back to class. So today we're going to get started back on this slide. We mentioned a few details in this slide last time, but let's kind of start over on atomic weights. The first thing is talking about the atomic mass unit scale. We've seen the AMU scale used on one slide where we were comparing the mass of the proton, neutron, and electron. We saw that the neutron and proton mass were slightly over 1 AMU each, and the mass of the electron was a fraction of an AMU. Now the connection over to a more common mass scale, we could give the conversion factor, because it turns out there's just a simple conversion for a gram of anything into the AMU scale. So the AMU scale is just really a mass scale, just like gram is or pounds is, with a relatively simple conversion. And it turns out that the conversion of 1 gram into AMU is actually a number you've probably seen before, that the number of AMU in a gram turns out to be Avogadro's number, if you've seen this number, I'm sure. So it's 6.022. We could look up more digits if we want to, and then times 10 to the 23 AMU. So it turns out there's an Avogadro's number of AMU precisely in 1 gram. Now, this is very intentional. We'll talk a little bit more in chapter 3 on why this is the case and how this came to be. We'll see kind of here down below, when we're talking about carbon, that the AMU scale is actually defined off of the mass of carbon. So you take the actual mass of the 12 AMU, one single carbon atom. You take the actual mass of that atom in grams, and you set that equal to 12 AMU. Because it contains about 12 protons and neutrons, makes sense on why we're defining that to be 12 AMU. But we'll talk a little bit more later on the connection between a mole of a substance, Avogadro's number for the particles in the substance, and then how that relates back to the AMU scale when we get into that topic again in chapter 3. But for now, we see that that's just a conversion between AMU and grams. We mentioned before you can usually give conversion factors both ways. You can say how many AMU are in a gram. You can also say, well, what's the mass of 1 AMU? So if we simply divide both sides of this equation by Avogadro's number, then we would get that 1 AMU is equal to a really small number of grams. It's 1.6605, some extra digits if we want, times 10 to the minus 24 grams. So 1 AMU is a very small mass, as you would imagine. And so now what we really want to talk about in chapter 2 is how we can understand why each element on the periodic table has a mass listed with it and what that mass corresponds to. The mass listed on the periodic table corresponds to the average atomic weight of all the naturally occurring isotopes of a given element. We had this equation last time that looked like this, that the average atomic weight was equal to the sum over I, where I is all naturally occurring isotopes, and we sum up the fraction of the abundance of that element of each of the isotopes. You can imagine, like we did an example last time where chlorine was about 75% one isotope, 25% of a slightly heavier isotope. So we would take 0.75 as the fraction for the one, times the atomic weight of the lighter isotope, and then it would be about 0.25 times the atomic weight of that heavier isotope. So you're taking the fraction of each isotope times the atomic weight of each of those natural occurring isotopes and simply summing those up. And it's the, if you will, the weighted average of all those natural occurring isotopes. Now, we don't have to memorize or know, like I wouldn't expect you to memorize that chlorine's has two natural occurring isotopes. It's not worth memorizing. Some elements like iodine turn out to really be predominantly just one isotope. I don't expect you to know that or remember that. But some elements will exist predominantly as one isotope. Some is 2, some is 3, some is 4. I think copper has like 4 common isotopes. So it really just kind of depends on a lot of factors. It really depends from, if you go all the way back to the Big Bang, on how the elements were created and then how they're still being created today from radioactive decay pathways from heavier elements. So there's a lot of presence of different isotopes that come from the decay pathways of other substances that are undergoing decay pathways all the time. And so for carbon, we can go through and try to calculate its average atomic weight just as an example to see how we use this expression here, because we're just doing a weighted sum here of all of these natural occurring isotopes. So for carbon, Two primary isotopes contain most of the abundance of carbon. Carbon-14 is a very, very small trace. So carbon-14 has an abundance that's less than 10 to the minus 10%. So carbon-14 comprises a very, very tiny fraction of a sample of carbon. So small, we wouldn't even need to consider that mass into the problem for the average atomic weight. So you may be thinking for carbon, when I say it has two natural occurring isotopes, you may say, well, I think it's 3. It practically is 3, but the third is so small and so small of a trace that it's almost not even needed to be thrown into this equation here. And so really small percentage is carbon-14. So if we're calculating the average atomic weight for carbon, the way I would do this is I would take the percentage, but as a fraction. So I would take the fraction of the one isotope. Now, carbon is very peculiar in that this is an exact definition. Like the mass of carbon-12 is defined to be exactly 12 AMU. So if we're like counting sig figs here, this is one of those infinite sig fig numbers where there's an infinite number of sig figs, not 2. So if we think about doing a sig fig problem here, I'm really looking at the 4 sig figs here being my limiting number of sig figs. But that's just kind of peculiar for carbon because it's the element that this scale was devised off of. And then we can add to that 0.0107. So just taking the percentage, but as the fraction, so just dividing by the 100% to express the value as a fraction, and then times 13.0034 AMU. So if we think about how the math works here, let's actually do this so we can think about the sig fig problem along with the actual atomic weight problem. If I do 0.9893 times 12, I would write this to be 11.87 to 2 sig figs, or 2 decimal places, so 4 total sig figs. Okay, and again, the reason why I'm not rounding to 2 sig figs is because 12 AMU is exact. So think of that as 12.00000 with an infinite number of zeros. And so it's the 4 sig figs that's limiting my result here on the multiplication step. And then I'm adding to that 3 sig figs times 6, so the 0.0107. Times 13.0034 is 0.139. And that's only good to the 3rd sig fig in that value. So then when I do my addition, I have hundredths place plus thousandths place. I'm rounding to the greater value placeholder, which is the hundredths place. So if I add these up, this would come out to be 12.01. But that's the average atomic weight of carbon in this AMU scale. So these are all in AMU, the atomic mass unit scale. Now we could convert this to grams. I don't think it's worth doing that. You'd see it's just a fraction higher, just of a really small number of grams is what we would obtain. Okay, so that's the idea of average atomic weight. If you look for carbon, we see that it's 12.011 here. We could look up a more precise, if we had slightly more precise abundances, we could come up with a more precise average atomic weight. So this is just in the limit of this data that we have in this problem here. So if you look up carbon in a CRC, you can probably get 6 or 7 placeholders on this average atomic weight. Okay, so we had mentioned before that for chlorine, and for atoms and really for carbon, other elements, that the way you would determine the abundance data and the average atomic weight data is through a mass spectrometry experiment. So you put a slight charge on each of these atoms. You have chlorine plus, but depending on the mass of the nuclei, the lighter the atom, the more it would bend in the magnetic field. So you can vary the strength of the magnetic field to then detect and count up the abundance of each of those isotopes. So this is kind of how experimentally the ratio of about 3 to 1 for chlorine was determined. So we're told here as a problem, bromine exists predominantly as bromine 79 and bromine 81. Their atomic weights are listed. You see that 79 being the mass number, we have roughly 79 total, not roughly, exactly 79 total protons and neutrons for that atom. And those are approximately 1 AMU each at rest. And so you would expect that for most atoms, the average atomic weight of a particular isotope would be pretty close to that mass number. But you see it's not going to be ever the exact sum of the neutron. We mentioned this before. You can't just sum up the proton's mass and the neutron's mass because those are resting masses. The nuclei have some stability that lowers the mass of that atom. But so we have bromine 79, 81, close to those atomic weights of 79 and 81. If we look up the average atomic weight of bromine, so if we look in the periodic table, it's 79.9 is what's listed. If I look. For bromine, 79.904. So this is what I get from the periodic table. So if you know one isotope is about 78.9 and the other isotope is about 80.9, on average, bromine turned out to be about right in the middle, 79.9. So what do you think the abundance is of bromine 79 and bromine 81? Probably about 50-50. So if we had about half of this isotope and about half of this in a natural sample, then we would arrive at an average atomic weight that's roughly in between of those two values. If bromine was like 99% bromine 79, then the average atomic weight would have been almost 78.9. Likewise, if bromine was 99% the heavier isotope, the average atomic weight would have been closer to 80.9. So you can get a sense of, if you know there's two isotopes, one's here in mass, if the average is in the middle, then we got about a 50-50 ratio of the two. And so I hope we can see here that the best answer here is, does the sample mostly exist as bromine 79 or 81 or about 50-50? That it's about 50-50. Chlorine, where we were looking at chlorine plus here, but here we're thinking about Br2, but two bromines. And so then if we're looking at a mass spectrum of bromine 79 and 80, if we were looking at that mass-like spectrum like we saw for chlorine, what do we think something for Br2? So imagine you have two bromines that are paired together with a positive charge, and we're looking at the mass spectrum. Kind of like and the thought here would be that if I have two bromines, I could have bromine with two 79s. I could have bromine where one's a 79, the other's an 81. I could have another where I have an 81 on the other bromine and then a 79 bromine on the other. And then lastly, I can have both of the bromines being bromine 81. It's like there's two isotopes, so either one of the bromines can be either one of those two isotopes. And so if we're looking at the mass spectrum, I think we could agree that these two would have the same mass, so the two in the middle would have the same mass as each other. And then the lightest would be this. The heaviest would be the bromine 81s, and these would be in the middle. What do you think their ratios would be? Like if we're looking at a ratio of what would be about, the first one would be about 158 AMU. This about 160 AMU, and then the last one would be about 162 AMU. What do you think the ratio we would see? Would we have like 1 to 1 to 1 ratio? I think we'd have 1 to 2 to 1. What do you guys think? Well, the issue is that we're 50%, like we're like 50-50 bromine 79 versus 81. So like if one of these is 79, then it's probably a 50% chance that the other one's going to be a 79. And if this one's an 81, there's like a 50% chance the other's going to be an 81. So it seems like we should be about 1 to 2 to 1. Does that make sense on how we're going to have probably double the mass in the middle since we have those two possibilities? And that's actually what we see here. If you look at a mass spectrum, you see about that 1 to 2 to 1 ratio. And so this is that one in the middle. This is that middle mass, the heavy mass, the lighter mass. And you even see in the spectrum, you see the bromine plus appearing as well with just one bromine with that 50-50 ratio. So you can get a sense of like what mass spectra would look like. You'll see some sample exam problems that will look like, well, what's a mass spectrum that you would expect to see for some given atom based on some data or based on its average atomic weight and how many isotopes that occur for it. And so one of the things that you're going to find is that most atomic weights of an isotope are going to be pretty close to a whole number of AMU, because atoms have to contain a whole number of protons and neutrons summed together. So you'll see some problems that look like mass spectrum problems, kind of like that one that we just looked at. Okay, so let's get into, we talked a little bit about the periodic table. We were talking about some of the different groups of elements. We were talking about the alkali group forming +1 ions. We're talking about the alkaline group forming +2 charged cations. We're talking about like aluminum forming a +3, and its group would, but really just aluminum is really the most common element in its group that forms ionic compounds. The metalloids are in the middle, have variety and sort of properties of both metals and nonmetals. And then our non-metallic elements on the right side, and also hydrogen. So that was kind of summarized here. So our alkali metals, that first group, lithium down through francium. Alkaline group, the beryllium magnesium group. The oxygen group takes the name chalcogens. I don't use that name too much, but it's kind of like the halogen group, but right before it for the oxygen sulfur selenium group. Halogens, the fluorine, chlorine, bromine, iodine group of elements. And the halogens are forming -1 charged ions. The chalcogen group -2 charged ions when they form ionic compounds as their common charges. And I really mention the charges just to get a sense of some property that the group of elements share in common. The idea from top to bottom is that those elements tend to be more similar in properties than from left to right. So fluorine and chlorine tend to behave more similar to each other than oxygen and fluorine do. So being in a group together allows the elements to share more similar properties. Of course, the noble gases all being the only group of elements that exist as monoatomic atoms in the gas phase, as stable atoms, is that property that they share. So helium, neon, argon, krypton, etc., existing as those stable monoatomic gases. Okay, now for most of the other elements that aren't the noble gases, they have to form compounds to have some sort of stability. We don't tend to just see hydrogen atoms floating around in the atmosphere or oxygen atoms. We see O2 as or oxygen is O2, nitrogen is N2. So molecules, or excuse me, elements will find some stable sort of form to exist in. We see a lot of organic compounds exist with carbon with 4 bonds, the most simplest of those compounds being methane. So methane exists with 4 bonds to hydrogen. That just is for carbon, what gives it the most stable type of compound. We often see carbon with 4 bonds, like for those who've gone to OChem. If you're drawing like a molecule and you have to put 5 bonds on carbon, probably made a mistake somewhere. If you only have 3 bonds to carbon, again, probably a mistake. So carbon through 4 single bonds is obtaining those 4 bonds. Like you'll see, like formaldehyde has a double bond to oxygen. So for things like formaldehyde, you get the 1, 2, 3, 4 bonds this way. We'd get the Lewis structures later in the class, but this is just kind of a couple examples of Lewis structures you may have seen before from your past courses where you can come up with some idea for carbon. Okay, having like 4 lines either through 2 doubles and 2 singles or 4 single bonds is going to be common for that element. And so we have different representations. Like we'll get into the 3-dimensional shape when we get to chapter 9 and talk about how it is that we know or how it is we can predict the structure of something like methane should be tetrahedral in shape. But for now, I think we can appreciate that we can write formulas. We can maybe sketch a Lewis structure. We'll see Lewis structures in chapter 8, so you don't have to know how to draw a Lewis structure yet, but you might see a Lewis structure and you can interpret a formula from it. From the formula, you can sort of get a perspective that there's probably some 3-dimensional shape. If you don't know the 3-dimensional shape, we'll learn that in chapter 9, but just getting a sense that molecules do have some 3D shape. And then there's also space-filling models. You don't see these too often, but you can make like a space-filling model and then interpret something about the structure of how there's still 4 hydrogens and a central carbon. Now for most compounds, you could write, what's the molecular compound, or excuse me, what's the molecular formula versus what's the empirical formula. So for CH4, that would be the molecular formula of methane, but then the simplest ratio of carbon to hydrogen would still be CH4. if we had another hydrocarbon, ethane C2H6, so that would be the molecular formula for ethane. We'll pick up some nomenclature for compounds as we proceed through the rest of the chapter. But we'll see that CH4 is methane, and then C2H6 is ethane. The empirical formula of ethane would be CH3, so this would be the empirical formula of ethane. Now, there's really nothing special about an empirical formula. Like if I told you the empirical formula of some molecular compound, it really wouldn't tell you much. What you really want to know for a molecular compound is the molecular formula. You really probably want to know the molecular structure and how the atoms are connected. It turns out that ethane gets those 4 bonds to each of the carbons this way here. So like sketching a Lewis structure or some interpretation of the 3D shape, that's really what you would want to know about a molecule. And the empirical formula is really not all that telling of a compound. It really doesn't tell you anything about the properties, because you could see 2 different compounds might share an empirical formula, but then have totally different properties. And so like if you were to look at, for example, ethylene is C2H2, and then benzene is C6H6, but then they share the empirical formula of CH. So if I told you some compound had an empirical formula of CH, you would say, well, it could be probably 100 different compounds. It could be ethylene, it could be whatever C4H4 is, it could be a variety of different compounds. So if you just knew the empirical formula, it doesn't really tell you much. The molecular formula and the structure tell you everything about the compound, and then that's going to be the substance that has some type of intensive properties, some common boiling points, melting points, physical properties. So ethylene's like a gas at room temperature, benzene's a liquid. So it really depends on how many atoms are connected together in terms of the properties. Now, predicting properties is not something we can do yet. That's, as you go throughout Gen Chem and OChem, you'll start to have some predictive understanding of some different physical properties of substances. So this is really picking up what an empirical formula is, the simplest ratio. Now, if we were to look at a different flavor, we mentioned way back on, I think, the second lecture that ionic compounds were a little peculiar in that we write things like NaCl, but the real structure of NaCl as a solid is like these alternating ions, where the structure is really millions of ions that are all linked together. That's why your ionic compounds exist as crystalline structures. That's because they have this network of ions and how they're connected together. And so for an ionic compound, really the only representation is that empirical formula, that simplest ratio of the ions. So like sodium 1 to chlorine 1, so NaCl. If you see a different compound like calcium chloride, where calcium's a 2+, so calcium's going to have to balance out its charge with 2 chlorine ions. And now it's going to do this millions and millions of times, right? Like you're going to have this alternating +2 with 2 minuses on either side. You're going to have this repeating throughout the structure of calcium chloride, but the simplest ratio would be CaCl2. So for ionic compounds, their best representation is through the empirical formula. So for CaCl2, you could probably say, I'm sure there's a crystal of like calcium 1,000, chlorine 2,000, but we just would always call that CaCl2. And it would have basically the same properties as calcium chloride. So like calcium chloride, depending on no matter how many plus and minuses you have, the ratio will be 1 to 2, and then the properties will be mostly the same. So we don't have this issue with with ionic compounds like we do with the molecular compounds. So ionic compounds, really only the simplest ratio of the ions is the only type of formula that emerges. Molecular compounds, we have all kinds of formulas that can emerge. Okay, let's do another sig fig problem. This is just kind of one randomly thrown in. I think sig figs is that one topic from like chapter 1 that will need some review. Let me just throw this to you guys and we'll look at this after a minute or two of your attempt. All right, let's talk about this one. I don't know if everyone's come to a consensus on their answer yet, or to their answer. How many people think it's B? I think it's B. So B is kind of the trick answer. That's actually not the right answer, because like B, you might think it's B because we know the multiplication rules. We're going to round to 2 sig figs. So if you see multiplication and you see 2 sig figs, you may think that we're going to round to 2 sig figs. It's not always going to be that simple. We have to use that rule on the multiplication step. So when I do the multiplication, 0.00015 times 54.6, that result has 2 sig figs. So the 0.00819 is good to 2 sig figs. And so that happens to fall in the tenths, hundredths, thousandths, 10,000ths place in the value. And then when I add that to 1.002, which is good to the thousandths place, what we're going to do is we're going to round this to that placeholder. So when we add, we follow the addition rule and we look at the placeholders, and we notice the greater value placeholder is this thousandths placeholder. And so that would be this placeholder here. So one thing you can always do is you can always just put this in your calculator, get your answer, and then try to figure out where to round it, so that you're really just rounding off once in that end step. And then we're going to round it to that thousandths placeholder here. And so that'd be answer C. Okay, so I think multiplication rule, just don't let the multiplication rule trick you on the addition rule. So we just have to follow the addition rule when we add, the multiplication rule when we multiply. Let's do one other review problem that just kind of entered my purview. Like the one thing from chapter 2 that sometimes if we don't practice it, we'll forget is the proton, neutron, electron counts. And so we mentioned bromine plus earlier, so let's do bromine 81. So for bromine 81 with a positive charge, how many protons, neutrons, and electrons? And we can do this together, I suppose, just as a reminder. The one particle, what's the one thing we look at the periodic table for? Which of those 3 particles do we get off of the periodic table? The proton. So that's the easiest one to get from the periodic table. So and we just look for the number for bromine, that's 35. So we have 35 protons, and then 81 is the sum of the protons and the neutrons. So if you take 81 total of those particles minus 35 gives me the neutrons, which would be 46. And then do I have 34 or 36 electrons? 34. So we've taken one away. So if I take one of the negative particles away, I have the net positive charge. So I have more protons. So I have 35 pluses, but only 34 minuses. So a net plus. I mentioned before, you can put an equation to it. I don't like equations. I just like the thought more plus than minus, overall plus charge. If we had the same problem, but 81 bromine with a negative charge, then of course this would be the 35 protons, same count of neutrons, but then the 36 electrons, for one more electrons than positive particles. One thing I also wanted to mention is if I just said, you have some other atom, like you have chlorine minus, like let's say, in some other example, you have chlorine with a negative charge. You could come up with the proton count and you can come up with the electron count, because we could look at the proton count from the periodic table, 17, one more in terms of number of electrons, so we have 17 protons, 18 electrons, but then we would not necessarily know the mass number. So we can't just know how many neutrons there are unless it's given in the problem. So if we were to say for some atom without a mass number given, you couldn't count up the neutrons because you wouldn't exactly know what the mass number was for that particular atom. You wouldn't know, if we just said sulfur, you wouldn't know how many different isotopes of sulfur exist as, which is the most abundant. You wouldn't know that information. Okay, so the rest of chapter 2 is really on naming compounds, and it's also a little bit, I think, on classifying compounds, because if we want you to name things like ionic compounds or acids, what we call binary molecular compounds, and then simple organic compounds, we have to recognize and best classify a compound into one of these categories. And so it'll kind of go like this, where if we say NaCl, like you may look at this and say, technically this is a binary compound. A binary compound we'll see is a compound that contains two different elements but in any proportion. So a binary compound could be something like NaCl, could be something like CO2, could be something like CO. But NaCl is an ionic compound, so it's not fitting for that molecular compound. So it's not a binary molecular compound. It's going to be best named for being that ionic compound. So you may look at a compound, you're going to try to say, which of these categories is it best fit into? Now, as we start going through examples, you may learn more about what it means to be an acid. You may not know right now what it means to be an acid. But as we go through the nomenclature system, we have to kind of come back and check the system for when I give a compound like HCl and say, name this thing, you may look at this thing and say, well, that looks like a binary molecular compound, but it turns out it's going to be more representative as being an acid. So we're going to see that that's more representative being in the category of being an acid, hydrochloric acid. So when you look at a compound, you're going to think, which category does it best fit into, and then how do I name it accordingly? One last example that we already saw a name of was like CH4. CH4 technically is also a binary molecular compound. It contains two elements in the proportion 1:4 ratio. So we could call this thing like carbon tetrahydride or something, but we don't. We call it methane because it actually fits in the category of being an alkane better than it does fit into the category of being that sort of simple molecular binary compound. So we call this thing methane. So again, not telling you these names here so that you could know all these systems, but as we learn about naming ionic compounds, we're also trying to recognize ionic compounds to name them as such. When we learn about acids, we're going to try to learn about acids and recognize acids to name them as such. When we learn about alkanes and hydrocarbons and their alcohols, we're going to try to recognize those and name those into those categories. So we mentioned ionic compounds. This is a representation of NaCl, kind of that repeating plus and minus charge. You see the minus charge for the green atoms, the plus for the sodium. Now, whether or not the ions will have a particular 3D arrangement that we may not be able to predict, like this example here shows the ions being kind of in a head-on-head arrangement. Whether or not they're head-on-head and the atoms are skewed relative to each other, that's discussed a little bit in chapter 12. So you may not really be able to guess the three-dimensional picture for ions, but you can get the concept that the ratio of the atoms should be 1:1. That if we were to count up the green versus purple, that should be coming up the ratio of about 1:1. And then if we had calcium chloride as an example, you may not really know what it would look like exactly, but that just whatever it looks like would have a ratio of 1:2 for one calcium for every 2 chloride ions. Now, the way sodium chloride would exist, and why it exists as sodium plus, sodium minus, is sodium on the periodic table has that one extra electron. Chlorine, if you've seen the dot structure, kind of is one electron deficient of an octet. So chlorine says, I'll take that electron, thank you very much. So you keep a positive charge, and I'll just take full possession and keep a minus charge. And so that's sort of the existence of ionic compounds are predominantly from the metals that want to give up electrons most readily and the nonmetals that want to accept the electrons most readily. The reason why you don't see this predominantly for things like CH4 is because the elements have a stronger desire to keep their electrons, or it takes too much energy for them to give their electrons totally up. So if you look at CH4, carbon on the periodic table has 4, and this kind of comes up in chapter 8 later, so you probably have seen this before, though, the Lewis structure of CH4 emerging from hydrogen's 1 electron, the 4 valence electrons on carbon pairing up and sharing this way. So that's a nice picture for CH4. Now, why does carbon not just lose the electrons? Like, why does hydrogen not just steal the electron to go to like H like this? So why not this? Well, carbon doesn't want to give its electron up. So carbon wants to keep those electrons, so this doesn't happen here. So this would be what it would look like if the hydrogens all went minus and carbon went 4 plus. You could also say, well, why isn't carbon ionic the other way? Why doesn't the carbon steal the electron from hydrogen and do this and have H pluses? Where carbon's a 4 minus. Again, hydrogen's like, no, you're not taking my electron, I want to keep it. And so, but for sodium chloride, sodium's like, fine, take the electron, I don't want it. And then chlorine's like, fine, I want it, and I have a stronger desire. So it's all about, we'll see as we get into chapter 7 later, that different elements differ in their desire for obtaining an electron, and then elements differ in how much energy it takes them to give up an electron. And for metals and nonmetals, perfect pairing for easy to lose an electron, happy to accept an electron. For the nonmetallic elements, takes a lot more energy to take the electron off hydrogen. Likewise for carbon, so this doesn't exist either. So we share the electrons through covalent bonding. So the sharing of electrons, the mutual beneficial, sharing of those electrons is covalent bonding. We'll talk about this more in chapter 8. Okay, so now what are some common ions? We talked about most of these already. So we talked about the alkali grouping plus. Hydrogen's not really a metal, so we don't classify as being an alkali metal, but it also forms a +1 charge if it's going to form an ion. We think of ions of hydrogen often in acidic solutions, so you might think of how HCl in solution is really H plus and Cl minus when they're dissolved in water. That's in chapter 4 that we'll talk about the actual behavior of acids. You talk about, I'm sure some people in the room have seen the equilibrium problems of calculating pH for strong acids and strong bases, and weak acids and weak bases. Who remembers solving for like the pH of an acetic acid solution? Anybody remember that? That's like chapter 16 and 17 later in Chem 1220. And so for now, we're just trying to pick up what are the common charges. So +1 for that alkali and hydrogen group. +2 we mentioned earlier for the alkaline group. There's the aluminum with the +3. And there, again, we were talking about this earlier, just on how the other groups in the aluminum part of the periodic table just tend not to form ionic compounds. And then nitrogen 3-, O2-, halogen groups a minus. We also see H can go minus. There's some compounds that look like this, like CaH2, where in this case here, hydrogen actually was accepting of those electrons from calcium, going calcium 2+ with H-. So hydrogen can exist with a minus charge in some compounds called hydrides, where it pairs up with metals. And then we have the fluorides here. So fluoride, or the halides, I'm sorry. So fluoride, chloride, bromide, iodide, sharing that -1 charge. And so we're asked a question here, what is the formula between oxygen and a manganese cation that has a 5+ charge? Now, if you notice, the transition metals aren't shown because they actually can have a variety of charges that aren't easy to calculate. Like for manganese, manganese is the 5th across on the transition metal block, so it's right here. And now based on where manganese is, if you were following the kind of rule from magnesium and sodium losing 1, magnesium losing 2, you might have thought manganese would be most happy with a +7 charge. And I do think manganese can form some compounds with a +7 charge, but it'll also form some compounds with a +5, it'll form some compounds with a +2 charge. It really depends on a lot of properties of manganese that aren't so easy to tell just from the periodic table placement. So we're not going to predict most transition metal charges for the metals. What we're going to do, though, is we're going to build a nomenclature system that we either tell you the charge of the metal or you can infer it from other information in the formula. So if we tell you manganese has a charge of +5, and it's pairing up with the common ion of oxygen, the common ion of oxygen is O2-. Whoops. O2-. So the charge of oxygen is 2-, the charge of manganese is 5+. What we need to do is put these into balance. We need to think how many of each of the ions are there going to be such that the overall compound is neutral in charge. And so there's a couple ways you can think about doing this. One way is this simple, just do this approach, do manganese 2, oxygen 5, and then you can double check the charges. So if you have 2 + 5 ions, that's a total of a +10 coming from manganese. And then the total for oxygen being -2 for each, 5 of them would have a charge of -10. So compounds should be charge neutral. If you don't have a charge neutral compound, you're probably going to have a thunderstorm at some point, so it's going to find the charge somewhere. So things tend not to exist with a net positive charge or net negative charge in like a bottle. So like if you think of having some sodium ion in solution, it's going to be paired up with something to counterbalance the charge. We're not going to ever have a bottle that just has, like a bunch of calcium ions without being paired up with some minus ion to balance out the charge. So whenever we give a formula charge, it has to be neutral. So compounds should have a neutral charge. Now the other approach, if we didn't want to just do the cross, kind of like the 5 of manganese over to oxygen's count and the 2 for manganese over to, or the 2- for oxygen over to manganese count, we could have just did, well, for 1 manganese, how many oxygens would it take? 2.5. We don't want to have a half. So the next multiple of manganese could be 2. So if I had 2 manganese, that would be a plus 10. I would need 5 oxygen. So we could have done the math the other way around to say, well, if I know I have to at least have 2 of the 5 pluses, takes me to a 10 plus. I know oxygen's a 2 minus, so that's how I can come up with a 5 here. So I can come up with the count on oxygen either through inference. If that didn't work, I would triple manganese, quadruple. I would just keep using a multiple of a whole number on one of the ions and figure out how many the other would put it in the charge balance. Right here on the periodic table, to be fair, I don't know why this is on the list that they want you to know, because I think I wouldn't have predicted that zinc, being where it is like the last transition metal element in the first row, only forms a plus 2. But for whatever periodic table, so silver is just right, like kind of catty corner, if you will, to zinc only goes with a plus. So then here's a quick little summary, and there's going to be a few other cations in this chart that we'll talk about when we look at this chart here. So we should know those main periodic table placement cations and their charges of the alkali, alkaline, and aluminum. We pick up zinc. Zinc is actually they want us to tell you guys that zinc only forms a plus 2. So if I say zinc, we will infer that it has a plus 2 charge. So zinc ion, only possible ion plus 2. Likewise, silver, so where's silver? Okay, and so then all other transition metals will use a charge system where we use a Roman numeral. So manganese 5 would be manganese with a plus 5 charge. So if we're going to give you like a manganese compound and name to have you write the formula, I might say, well, what's the formula of manganese, say 2 oxide? So manganese 2 would imply that the charge on manganese is plus 2. So that would imply Mn plus 2. That would just pair up with O2 minus for MnO. So for transition metals that aren't silver and zinc, we're going to tell you their charge as a Roman numeral in the name, if we give you the name. And then if we give you a formula from which you can deduce the charge on the metal. So if I give you a compound like this, if I give you Cu2O. So for Cu2O, we know oxygen's still a 2 minus, that's its common ion. And then we have a 2 minus or minus 2 charge coming from the oxygen. 2 coppers have to have a charge of plus 1 to balance out that charge. So the 2 coppers together have to be plus 2. There's 2 of them, each has to be plus 1. So Cu2O would be copper 1 oxide. So notice that the 1 isn't implying how many copper there are in the formula, it's implying the charge of copper we can deduce from the formula. And so then lastly, just to give an example like zinc or silver, like ZnO would just be zinc with a 2 plus, oxygen 2 minus. So this we would just call zinc oxide instead of zinc 2 oxide. If it were up to me, we would just call it zinc 2 oxide, so that we would just always, for all transition metals, use a Roman numeral. But the only 2 that we're not going to use a Roman numeral for, and if we use by name, it would be silver with a plus 1, zinc with a plus 2. So one last example to use silver. If I had silver chloride, the implication is, or the idea is, that we just have to know then, if this is like on a test, we'll have to know that silver is Ag plus, chloride's common ions minus, so that would just be AgCl. Now, there's one other peculiar feature with mercury, but let's get to that in 1 second. So we also see ammonium is NH4 plus. We've probably seen this before for like ammonium salts, like ammonium chloride, ammonium nitrate. Hydronium is this sort of a form of writing like H plus dissolved in water. So you might have seen H3O plus. So this is often just H plus in water, how it's represented in a formula. We call it hydronium. And then we get a weird case with mercury compounds where there's this weird compound that emerges for mercury where you have 2 mercury atoms bonded together with an overall charge of plus 2. So this kind of looks like something like this. I'm not entirely sure what the bond, there's some metal-metal bond between the mercury, so I'm just like, there's some sort of chemical bond here. And then the overall charge on this entire group of 2 mercuries is +2. So you would think mercury 1 would be Hg plus from the usual nomenclature system for Roman numerals. So you would think mercury 1 would be Hg plus, but it's not. So mercury 1 is not Hg plus, it's Hg2, 2 plus. So you see it's on average mercury with a plus charge, but just where you have 2 of them with a 2 plus charge. So this is some molecular ion involving metals. So what this means is if you have mercury 1, say bromide, that mercury 1 would be Hg2, 2 plus, and then that would be paired up with 2 bromides to balance out the 2 plus, 2 minus. And so now, I would actually call this the empirical formula of this compound. Now you may say, okay, the actual empirical formula is HgBr, but I would say ionic compounds, we usually express them as the empirical formula of the ions, the simplest ratio of the ions. And so the simplest ratio of mercury would be Hg2, 2 plus. So we can't really break that down further since it's bonded together. It's kind of like if you've seen the example, and we'll see this a little bit later, of peroxides. Like peroxide ion is O2, 2 minus. So the simplest peroxide ion is O2, 2 minus, not O minus. And so if this pairs up with, say, sodium, we're going to get sodium with a plus charge, 2 of them to balance out the charge. And so I would still say that this is actually the empirical ratio of these ions. Maybe not the empirical formula, but the simplest ratio of the ions in the compound is how we express the formula for ionic compounds. So Na2O2 for sodium peroxide. We'll pick peroxide up when we get to the anion nomenclature in a minute. But mercury kind of looks like the example that peroxide is on the anion side. And you may have seen the peroxide ion before. Note that mercury 2 is just the ordinary mercury 2 ion. And what's weird with mercury is that these are the 2 common ions that mercury exists as. So mercury 1 with Hg2, 2 plus, and then mercury 2 is the ordinary Hg 2 plus. And so the red system just kind of matches the rule. So the red on these slides is kind of like by rule or convention how you can pick up the charge in the name. Like the alkalis, just periodic table placement tells us they're +1s. The alkaline group, the magnesium group, the periodic table placement's telling us a +2. I really don't have to memorize that. I just know it's 2 over from the periodic, from the noble gas count. Aluminum's 3 over, hence a 3 plus. And then mercury 2, by analogy, if we had mercury 2 bromide instead of mercury 1 bromide, that this is just Hg2 plus, Br with a minus, 2 of them to pair up the charges, so just HgBr2. So Hg2Br2, HgBr2, so mercury 1 and 2 bromide do exist. They actually differ in property. I think the only reason we're even telling you about this case with mercury here is that in chapter 4, the mercury 1 salts have like a different solubility rule than the mercury 2 salts. And we'll try to understand. And if we just introduce then that there's these 2 compounds of mercury, I think it's even more confusing. So we may not do a whole lot of examples of mercury here in chapter 2, but we'll pick this up again in chapter 4 to see that there's actually a difference in properties of these 2 types of compounds. Okay, so the goal of naming, or naming conventions might be maybe three goals. One is just recognition. So when we see a compound, recognize it as a category. But then 2 is if we give you a formula, be able to name it. And number 3 would be if we give you the name, write the formula. So it's all about really name to formula, formula to name. It's not about predicting why some compounds exist. I'm never going to give you a question that's like, well, manganese, we said earlier, was +2, +5, or +7. Why not +4? I don't know, maybe it does form a +4. Like, we're not asking you to answer the why certain compounds exist or predict if compounds exist. No, just if we give you a formula, be able to write a name. If we give you a name, be able to express the formula. And so I think for ionic compounds, I think you can pick up the nomenclature pretty easily. Like we know this is sodium chloride, I think. And by know the name, like we don't call it sodium monochloride, right? We've seen NaCl before, we call it sodium chloride. MgCl2 is where sometimes you may think, is that magnesium dichloride or is that going to be magnesium chloride? And if you think about it, if I told you the name was magnesium chloride, do we need the di there? The answer is no, because we know magnesium's a +2, we know chlorine's a minus, and then to balance these out, the only possible compound is MgCl2. So I think the only reason we would ever need to call something magnesium dichloride is if magnesium chloride with one chloride could exist, and it can't exist. The only possible compound between magnesium and chloride is this one here. And so this would be the best name for magnesium chloride. And so we'll use the di, tri, tetra nomenclature system for other compounds later, like when we see CO2 versus CO. Like those are two compounds of carbon that can exist with oxygen. We have to come up with two different names. That's why one's carbon monoxide, the other's carbon dioxide. So for those binary compounds we'll eventually get to, we need the mono, di, tri system. We don't need those for ionic compounds. So what's the name of this one here? So if you're picking up the system, it's just metal name, the cation name followed by the anion name. So we haven't gone through anion conventions, and I know I write terribly, so let me rewrite this. That the common ion of oxygen is the oxide ion, so the common anion names end in the IDE suffix. So this one here would be sodium oxide. So notice I don't have to call it sodium 2 oxide, that would be wrong. I don't call it sodium 1 oxide because we know the charge, just sodium oxide. So what about magnesium nitride? What do we think the name is for magnesium nitride? Or excuse me, what do we think the formula is for magnesium nitride? So what's the charge of magnesium? +2. And nitride, the simple ion of nitrogen, would be 3-. So again, like we can either just do this system here, and that would work, but we could also then just do some math, +6, -6, two of them, -3 overall, so Mg3N2. So magnesium nitride, Mg3N2. So you should always be able to double check the charge going to neutral. And so the last slide we'll finish up on is the polyatomic ion. So ammonium, we mentioned one for the cation. So having 4 hydrogens, a nitrogen with an overall positive charge is ammonium. And then the polyatomic ion for sulfur, a common one, is with oxygen. So we'll see for the non-metallic elements, we'll see a lot of anions where we pair oxygens onto a given element. So sulfur most commonly forms this type of anion with 4 oxygens with a -2 charge. So that takes the name sulfate. And what we're going to try to pick up a nomenclature system for is if we systematically have SO3 but with a 2- charge, what would the name of that be? And we'll see that this name, with just 1 O less, just changes the ATE to ITE. So we'll try to come up with some systematic names for naming compounds that simply vary in the number of oxygen count in that ion. And then we'll pair these up with some other compounds so we can name other ionic compounds. All right, that'll do it for today. We'll finish up our nomenclature and other compounds on Friday. Have a great rest of your day.